Full disclosure, I am actively working on a safe product that will compete with other products I discuss in this video. My primary goal in releasing this video is to raise public awareness that as of August 2025, I'm not aware of any safe aftermarket lithium or sodium battery product being sold for any nickel metal hydride Toyota vehicle. To understand why, let's quickly review how the battery smart unit works in nickel metal hydride Toyota vehicles. They're all functionally identical. We're going to be looking at the Gen 3 Prius. That's what this electronics package is here. This is the battery smart unit, or the BSU. So let's see what it does. Inside, we have this connector here, which goes to your high voltage battery, and it is measuring 14 analog voltages in the pack. So that would be 1 minus, 1 plus, 2 plus, 14 plus. And it's important to note that we only measure 14 voltages in the pack. With nickel metal hydride, that's safe because the nickel metal hydride chemistry can tolerate that because of the way its end of charge curve is, which lithium and sodium cells are not the same. I've already discussed that in detail. This is not the video to discuss why it's not safe, but it's just to raise awareness that it is not safe. So we have 14 analog voltages coming in from the pack here. If you have a next cell sodium pack, then 1 minus could be here and 1 plus could be there. Or 2 plus on the next one, 3 plus on the next one after that. With the stock nickel metal hydride pack, because this is the width of 2 blades, the stock one will be measuring 2 blades worth of nickel metal hydride cells in series. With the next cell, I call this a 2x blade, you're measuring every blade in one spot. So this total blade gets you 1 voltage that the BSU measures. There are 14 blades in the Gen 3 Prius, which is why there are 14 channels that we are measuring here. So on the output, we are basically sending a serial data stream to another computer that's making all the logic. This doesn't really do any logic, it just tells the other computer what the voltage, the current, the temperature, the isolation, etc. are. So this connector here is just doing current, temp, and isolation, fault stuff, etc. But this guy is not really making any logic decisions, it's just forwarding all the voltage and current data to a different computer that makes that logic. So that is the BSU in the car. So next, let's recap the products I've previously reviewed, very, very high level. We'll first look at NextPower here. So the NextPower is the one that introduced me to this aftermarket world. I have made plenty of videos on this. Some version of this product is still being sold. There have not been any recalls, etc. But let's look at how this works. Inside, if you take the cover off, we have a BMS PCB that you shouldn't just rip out, but I don't really care, so I'm just gonna take it out like that. What is this circuit here? This circuit, I've drawn it before. It is an NFET open channel drain there that is connected in parallel with each cell, like that, and it has glue logic, which is basically a comparator that's saying, is the voltage of this cell greater than or less than some reference here? So that's the black box there, there's our ground. So basically, let's say this is 4.25 volts. This voltage changed between the different versions, but the functionality was always identical. Above some voltage, we turned on a resistor, and that resistor ranged from 20 to 80 ohms, doesn't really matter. And when we are above this voltage, we discharge this cell, period. That is it. That is all of the electronics in all of the LFP NextPower products. They are all functionally identical. What do I mean by functionally identical? They do some version of this, where we have an open drain here that turns on. This is literally a switch. This is equal to, you have a battery. We'll draw the battery like that. And you have a switch, and it has a resistor, and this switch is turned on and off based solely on the voltage of that cell and nothing else. If we are above that voltage, this cell is discharged into that resistor, and that is an attempt to balance cells. So I first saw it in this product. There have been multiple versions of this product. Here's actually an older one. This is the one I first saw here. And then they released a newer one, which looks like it does more, but it doesn't. It just sinks more current. Both of those were not adequate for that product. I've already discussed that for hours. That's not the point of this video. Recently, I reviewed this Huilian cell here. The Kapton is mine because I don't want to short this out. What does this circuit do? Well, it sure looks a lot similar to that one, and it sure looks a lot similar to the other one that I lost already. And that's because it is. So what does this circuit do? It's right there, drawn on there. It is identical. That circuit does this. It just does it, in this case, at higher current. I believe this was 5 amps. Don't quote me on it, but functionally identical. Yeah, that sounds like about 5 amps, 800 milliohms, yeah. So this cell here I reviewed last month, and yeah, this is not a safe product either. This one's using nice NMC cells. Those are the spiciest ones that you really don't want to overcharge. Okay, so that's the background on the cells I've looked at. Again, they're all basically this circuit here. And I want to show you, and I'm going to turn the camera sideways because I work in portrait mode on computers. So apologies if this is painful for your brain, but I'd rather there be more visibility and you have to turn your head sideways than to film this in landscape. Okay, so I have the Gen 3 Prius system here. That's gonna bother me, it's crooked. It's better. All right, I have the Gen 3 Prius system here. We have, each one of these vertically is one of these blades. Actually, this is the Huilian setup here because of the different chemistry here. So this is the Huilian setup, and each vertical stripe is one of these blades because there's 4 cells in here. If this were the next cell, this would be 5 tall, but it's only 4. None of the behavior I described changes because of that cell. It's just that some of the actual values change. So yeah, the vertical stripes are these blades, the Huilian blades, because they are NMC lithium, which run at higher voltage, so you need fewer of them. And in the Gen 3 Prius, we have 56 of them. So if you counted all these up, you would see 56 of these. And all the BSU is measuring on the orange connector here that I drew earlier, it doesn't know any of this. So what does the BSU see? It only sees this stuff at the bottom. So it sees 14 voltages here, and in this case they're all the same because all the blades are the same. Of course, the system can't see those blades, as I've already said. This will probably black that out better. That is all the BSU can see, is those 14 voltages. And that's the critical safety issue with a product that, these products that I've reviewed. And because we can only see 14 of these, we have no idea how these specific cells are. So for example, I'm gonna cover this here and see if I can look. Okay, so in this example here, our system is only seeing a 100 millivolt difference. So 16.3 volts here and 16.4 on all of the other ones. And yet we have a cell up here at 4.3 volts, which in lithium land is very high. That is basically the threshold at which things start becoming really spicy and dangerous. And if you'll notice here, what our system is measuring in our delta V tap, so the voltage tap that our BSU can measure, is only 100 millivolts different, and yet we have a cell here that's very unhappy. If you look in the Toyota service manual, one of their failure criteria for intermittent issues is that if you see above 300 millivolts on this delta V tap between any 2 blades, then you should replace the pack. Now, the system doesn't throw a code though until 1.2 volts. And so what you'll notice here is that no matter what this voltage goes to, if only one of the cells is misbehaving, we might go above this 0.3 limit, or we might not, right? But we can't really fail until 2 cells are failing. So like right there is on the threshold. And this is incredibly dangerous. This voltage is never going to get up to the 4.7 you see here, because at around 4.5, these cells are going to catch on fire or have a thermal event, if that's what you want to say. And above 4.25, you're really starting to be very, very dicey here. And again, all of this stuff is happening in the background. This is all the BSU sees, so we're happy, right? We're still happy here, we're happy there, even though when I move my mouse now, that cell has basically caught on fire. Now, of course, we're not going to get to a case where this cell catches on fire, but we could get in this state here where these are getting really close to catching on fire, certainly very, very dangerous voltage levels, and we're not catching in that at all. And again, this is with two cells. If you have one cell here, look, I've got a cell at 4.4 volts and the rest are at 4.1, that's really, really scary. And you may say, but wait, there are 8 amp cell dischargers active, or 5 amp or 1 amp, you know, depending on the product, the discharger. So this resistor here is maybe 1 amp or 5 amps or 8 amps, as we'll see later, or, you know, less than that, whatever. It doesn't matter. In this case, this cell's discharge resistor is on. I'm going to pull it down here. You can see that once we drop below the 4.25 volts, that we now have turned this guy's on. But again, that's only going to be up to 8 amps. And on some of these products, it was 5 amps or 3 amps. It doesn't matter because we can put 45 amps regen into here, and 45 is greater than 8 last time I checked. And so we're going to keep charging this cell. This system has no knowledge. We don't have any global observer, and so we're not seeing anything that would cause this defect. If you'll notice, I have an LED here for this POA80, which is the when we exceed 1.2 volts. And if you look, that never happens. Oh, ooh, look, we barely got there at 4.7. And again, these cells are never gonna get that high. The ESR monitor would catch this first. The cell resistance would go too high. Above about 4.5 volts, because your cell is literally about to catch on fire. The resistance is going to go up, the voltage is going to spike. But all of these voltages down here, 4.4 volts, very unsafe. The red, if you're unfamiliar, is very unsafe territory. 4.3 is also unsafe. At 4.2, which is where all these systems will sit, right? If we sit all of these systems, you know, here, there's no balancing happening. So if you're driving the car and you regen downhill and then you park the pack, you know, at 4.24 volts or whatever, these cells are going to just sit there at that really, really high voltage. It's going to really shorten your cell lifetime. Generally, you want to be running a pack like this in like 4.1 tops, 4.05, and certainly for resting, like 3.954 volts. That's going to give you the longest life in these automotive traction environments. The last thing I want to point out is this full regen allowed here. You can see that this is based on data that I previously showed, but can't find at the moment. Here it is. This is based on the nickel metal hydride operating voltages, and then I extrapolated that to a 5-cell in series and a 4-cell in series. We're looking at a 4-cell in series right now. This is NextPower's 5-cell. You can see that you know, up to 240 volts or so, we are still allowing regen pretty heavily. I found Chapman F said at one point he was able to see 45 amps of regen with a pack voltage of 262 volts. So let's see what gets us to 262 volts. It's pretty high. So I don't know, that might have been in a vehicle with different things. This is the data I've certainly seen. You know, we certainly allow full regen up to 235 volts. Oops, why did that scroll down? Whatever. So in this region, in the yellow region here, we have a limited regen, and then below it, we're allowing full regen. So right here, we can regen at the max amount, you know, 75, 80, I don't know what the max amount is, 100 amps, no idea. It's certainly greater than 8 amps. It's certainly greater than 5 amps, which these systems have. And so this is kind of a visualization trying to show what I'm seeing here. The last thing I'll note is that because we only see this voltage here, it's possible that you have a cell that's really high and another cell that's really low, and you don't see any difference at all because we don't have per cell control. And you know, you'd say, well, that couldn't happen. Why, how could you have one cell really high and one cell really low? This cell has failed. It gets really, really hot in use, but not hot enough to send POA80. And when it's above this, the circuitry, which is literally right stacked next to it, we'll look at another example in a second, it heats the cells around it up. So here's Huilians again, right? Like you're dumping all of this heat, 5 amps at 4+ volts, that's 20+ watts. Now you're heating up to the bad cell and the cell next to it. Well, what does the cell next to it do when it gets hot? If it's still good, it's going to have higher self-discharge because it's hot, and so it's going to discharge. And so this is a very, very likely thing that can happen. You have one cell that's failing, it's probably getting into the 4.4 volt range, and it's causing this one to drop down. And so the problem you run into then is that, yeah, you turn the car off and this cell has a charge and it's gonna slowly come down and eventually it'll get to here. What about that cell? That cell's discharged, so it's not gonna do anything. Okay, so then you drive the car and you regen more, and so now we regen up here or whatever, and say we get up to this 4.3 volts, which you can totally do because there's nothing, we don't have a global observer, right? Like this dumb circuit is only inside of the module, right? It's this thing inside the module. It can't talk to anything else. There's no global observer at all. And so this circuit here, look, once again, maybe this cell got up to here, and this cell, because it was weak, it probably got up to here, 4.5. Above this 4.5, the cells are really likely to catch on fire. So this top range here is more academic. But okay, so now you turn the car off. Well, what happens? Okay, so the dischargers discharge the cell to 4.25, and then this one's doing it in parallel, and it gets down to 4.25, and its balancer guy turns off. What happens to this one? Nothing, right? It just stays there again. And so we go through drive cycle after drive cycle where we are just absolutely ramming these cell voltages high. We're not getting any errors, right? Because we're not above the 1.2 volt limit. And this cell maybe charges to here. This one, of course, again, spikes high again. Okay, now you turn the key off. Well, what happens when you turn the key off? Well, we just discharge to 4.25 because we're a dumb circuit. We're a completely analog circuit. I don't know why this one changed. Okay, but you can see that we've now balanced here. That's the eventual thing, is that eventually the weak cell is going to balance up to this high voltage, but then we're going to just sit here at where this comparator turns off. Again, dumb circuit. This dumb circuit, it turns off below 4.25 volts. It turns on above. It doesn't do anything else. And so what the end result is that the worse shape your pack gets in, the higher these spikes are when you drive, and the more damage you're doing to these cells that are, basically getting overcharged, and then they're having to self-balance down, and as is this one. And then your weak cell, of course, because this guy's getting hotter because it's turning on the self-discharger, it's causing the internal leakage to increase there. So, the key takeaway from this graph here, I've described this same behavior multiple times in videos. I've never done it visually. I thought this could be useful for people to look at it, but even in this case here, where the pack is balanced or whatever, we were allowed to regen, and these packs are going to just sit high if you're regenning downhill. Now it could also be the case that you live in a flat area, you don't ever really regen, and your pack stays in a healthy spot, and maybe these stay in a healthy spot too, but the problem is we cannot detect any single cell failure, and that is absolutely required in these chemistries that are not nickel metal hydride or lead acid, or I guess nickel cadmium, but no one uses that. Obviously, I don't think any electric car has used that in production. Maybe, but anyway, except for lead acid and nickel metal hydride, you need per cell supervisory control. And if one of these cells gets unhappy, so let's say this cell gets unhappy because it gets to 4.2 volts, which would be a very good spot to say, hey, maybe we should stop charging. 4.2 is 100% state of charge on pretty much every lithium cell. And so, we could also dynamically say, based on the temperature, hey, let's limit it to 4 volts. And then at 4 volts, we could basically tell the computer not to regen. Don't apply any more regen. By the way, all of the stuff I'm saying here for regen also applies on the other end to assist. I'm not going to show that here graphically. It's functionally identical. It's just now you have a cell that's weak and discharging more than the rest. But, you know, functionally identical issues on that vein. So if you have other things you want to see on this, I can definitely show them in a follow-up video, so please comment. And if you have things where, you know, hey, I got this wrong on the Toyota whatever because it X, Y, and Z's, post about it and we'll look at it. You know, we'll see what that is happening. But basically, because we don't have a global observer that can look at all of these cells and make logic decisions on the fly. So with a global observer, with a properly, you know, supervisory control and data acquisition system, it would be able to see every cell and it could make programmatic limits based on temperature. You know, if it's below freezing, you could tell it, don't charge at all, because of course, this dumb circuit doesn't have anything about temperature sensors to say don't regen when the pack's frozen, which lithium does not like. So that is this GUI here. I hope it is useful. I know it is sideways here, but again, I program in portrait. All my monitors are in portrait. So let's get to the actual point of this video today. It's not just to dunk on Nextpower more. I've done that enough. And yet they still sell their product, but whatever. So I recently reviewed yet another dangerous aftermarket battery for the Toyota vehicles. This company actually contacted me, and I privately raised several safety concerns with their product, which I'll show now. I'm showing the circuit board here. And for now, I don't really feel any moral duty to reveal who this company is they're actually going to go back to the drawing board to address the safety issues I raised before selling their product to customers. So I was really happy that they were actually listened to my feedback and whatnot. So I do want to note, I have zero business relationship with this company. They haven't paid me 1 cent, and I am returning their review units after filming this video. So they did send me an entire pack. And I mainly just looked at one of them. I will be showing the inside of it, but not the outside, again, because they are actually going to try and fix these issues. Unlike Nextpower, who told me to pound dirt and then watched as their customers' cars had thermal event after thermal event. By the way, I am aware now of one Huilian customer whose pack has actually had a thermal event. So, you know, it doesn't surprise me in any way. So yes, I will not benefit financially from the contents of this video. I don't even have YouTube ads. I have them turned off specifically. But I do want to say that, sorry, I will not benefit financially from contents of this video, which are solely at my discretion. So no one has paid me to say anything. I am not even keeping this product. I'm returning it, etc. So my only potential financial incentive here is that, again, as I said at the beginning, I am actively working on a safe product that will compete with the products that I'm discussing in this video. So here's this new PCB. If you look at the silk screen on it, it has these two guys holding hands here, and what looks like you know, an integrated circuit that is doing some kind of logic here, maybe a global observer. And so when I look at this silk screen, which is just a pretty picture for people, it looks like we have supervisory control and there's a handshake, you know, there's a serial bus where we're having data. That is absolutely not the case. So this circuit here is unique to each cell. So every single cell gets one discharge. In this system, this is a 2-cell blade. So their blade width is 1x of the OEM, whereas this is a 2x blade. Theirs is the OEM 1x, and so inside they have 2 cells. This circuit only monitors that cell, and this circuit only monitors the cell that it goes to. There you can see the terminals here. There are 2 connections to each cell, and it's just a remote sense. So we have a current and then a remote sense. I don't know which one is which, it doesn't really matter. I believe this is the remote sense, B2 plus, B1 plus, B minus, and then the current is there. I'm not gonna really go into detail on it. These are functionally one wire hooking to each terminal there. Let's look at how this works. So I have a programmable power supply here, and I don't think you're gonna be able to see the voltage. Oh, maybe, okay. So let's look at this system here and see how it works. So I'm gonna start at 3.62 volts. You can see nothing happens, and I'm just gonna keep raising the voltage. You can see nothing happens, nothing happens, nothing happens, nothing happens, nothing happens. And why does nothing happen? Because this circuit is this same circuit with one modification, which we'll get to in a second. Okay, so right around here, we have fancy things that start to happen. So these LEDs should be blinking, but on this one they weren't. I thought that was funny. And on this one, I've destroyed the circuit to figure out what it is, because even though we worked with this company, they would not send me their schematic, so I had to reverse engineer it. They cover their circuit with epoxy, hoping that you can't get in there and see what it's doing. Funnily enough, though, because there's no compression on their existing product, this epoxy ends up gouging the cell because the cell is not under compression. So as the cell expands due to the gas that builds up because it's not under compression, it hits this epoxy first, which I just thought was a funny thing. Anyway, I was able to dissolve this with sulfuric acid and I guess dichloromethane, and also just some physical abrasion. And so their circuit, which they say is a battery management system, but it is not, is this circuit here, except they got really, really fancy, and they have another resistor with another MOSFET that goes to another comparator. I'm breaking that there. And so this other comparator here is the same, but it just has a slightly different voltage reference. So that hooks up there. I should have drawn this a little better, but whatever. So yeah, there's some reference I didn't draw. So there's R2, that was R1. So what is this? This is two MOSFETs in parallel. I'll draw it again in case that's unclear. So here's your cell here, and the other ones I've reviewed to date had one magic black box here with a comparator inside of it, etc., whatever. This new product, there's your resistor, has two of them in parallel, another black box there with another comparator there. So functionally identical circuit, and I'll show you that circuit here. One difference is they don't use discrete resistors. They actually just have resistors in this single-sided aluminum PCB, and I'll show you on a thermal camera here. We've had this on for a minute now. So you can see that we're looking at this circuit here, and you can see basically that we are just pulsing heat in there, and this is already at 50 C at 4.29 volts or whatever, because we're dumping 4 amps, so we're dumping 16 watts per cell. If both of these were on, again, I've destroyed this one, if both of these were on, then you would actually see heat there as well. But if I actually dial this down, you can see that at the beginning, this heat is, the comparators are at slightly different voltages, so that you first have like 4 amps and then later you have 8 amps or whatever. So you can see that only this half of the circuit board is on right now at 4.28 volts. But watch what happens as I turn this up more. We're gonna jump up to like 8 amps eventually. I think I might have broken this one. I was doing some abusive testing, but what you would see is that this other side will eventually heat up. But yeah, this board has been attacked with some pretty bad chemical solvents. But yeah, there should be a second half that's activating that's doing another 4 amps. One thing I did want to point out is that this board has no current limiting, no temperature sensors. So if you want to put 120 watts, well, you can see that something geeked out there, but we're pushing 100 watts into this board right now, and you can see that it's 102 degrees Celsius. We still only have half this on. This would be 16 amps otherwise, but there's no power limiting, there's no temperature limiting in this. This is the same dumb circuit as before in this new product, which again, this manufacturer, to their credit, decided after I worked with them to not sell this product. So I do commend them for that. So the last thing I wanted to talk about today is how do you know if you're buying one of these things? Because it seems like there's a lot of interest. There's a lot of companies, ooh, that's toasty. There are a lot of companies making these products, and it just seems like there's a lack of knowledge or safety in how to do it. I've talked about this a little before. In fact, with this specific module, I've talked about it before because I'm looking here, it actually has Sharpie on it, where I've drawn adding an extra pen. So let's talk about the number of pens that you need. Again, how do you know if your aftermarket lithium or sodium product is safe? The first thing is, if your battery has 2 or more modules, so in this case, ignore that for now. If your battery has 2 or more modules, then you need at least 1 extra wire between each module besides the current wires here. This is the bare minimum. So what is the bare minimum to know that your product is actually safe? And by safe, I mean you have some way, if any one cell is unhappy, right? If this cell gets unhappy here, you have something where we can catch that probably back here and alert the system. And how do you alert the system with 1 cell? So if you have an extra stud in this, for example, you could put an extra stud below this module here. So this would be where that little hole is there. And you could actually hook the OEM BSU wire harness. So this has a bunch of wires coming off of it. These are not the right ones, but this is just, you know, representative here. You could add another stud here that plugs into the BSU, and then all of these things they're on one continuous plastic harness. If these all plugged in down here, then in that case, your circuit board inside, which is certainly not this one, could basically scram the 14 voltage taps. So it could scram one of these voltages if anything bad happened. It would be a janky solution and a non-ideal solution, but at a very, very minimum, if you are putting a non-nickel metal hydride battery, lithium or sodium of any variety, inside of a vehicle that was originally nickel metal hydride, you need at least the 2 terminals per module that bring the current in and out of it, and you need at least 1 additional terminal that could indicate that you have a safe system. It's not a guarantee. I said could have a safe system, but this is the bare minimum hardware required for a potentially safe product. And I showed you that one example there where, you know, how would this work on the paper? So we have this extra stud here, right? So if we looked at our circuit board inside of here, it's not a global observer, so we can only look at the cells inside of this module, or maybe even just 1 cell. So here's our cell, that's a black box here. And we have the current going into it, and we have the current going out of it. So that's these 2 terminals right here. And I'm just drawing them flat conceptually. And if we added this 3rd terminal here, that this one goes to the BSU, where the BSU again measures the voltages. If you remember the BSU here, here it is. This BSU has 14 voltages. We're gonna hook one of these leads up to each one of those wires. And then inside of here, this is a very high level abstracted circuit. You could basically add our favorite little open drain here with some kind of resistor network of some kind, to where if something bad happens in here, we get above 4.2, or, you know, I don't know, what are we, below 3 point, whatever the cell is, then we can basically assert this line, and it will basically make a large enough voltage delta on here. So like it could basically pull this down to like 14 volts or up to 18 volts, or, you know, whatever it needed to do. That would be an analog, janky solution. But the benefit of it is that we could continue using the OEM BSU now in a safe fashion. But this would also need to assert on temperature. So like if it's below freezing and you need to tell the system not to regen, you could spoof the voltage. Now note that spoofing these voltages at some point is going to cause the POA 80 code. So you wouldn't have a lot of control as far as like, if you get in even a borderline unsafe condition, you might have to send that POA 80 code just to get the system to stop regenning. But that at least would be safe. So you'd probably have a lot of false negatives. Is that right? Yeah. But you know, whatever, right? It's better in these systems to fail even if you're not failing, right? To disable the system, you need to fail safe. If the system is unsafe, you need to be able to stop it. So that's the minimum you need. The bare minimum is you need at least one extra wire coming out of here, and it could be, you know, an extra stud here. That's a crappy solution though. So, you know, the main thing is with one extra wire, it's nearly impossible to become a global observer. You don't get all of this information in one place, right? You don't get to see all of the cells. You can only see at most the number of cells that are in your module there. And so like, what do you lose? You can't balance the cells really well. You know, you can only do fixed point, fixed voltage balancing, which is not good, if I didn't make that clear previously. So if you do want a robust global observer with supervisory control and data acquisition that can look at all of the cells, you really need at least 2 additional wires. And this is just a mock-up. I've taken the NextPower thing. If the NextPower module had 2 wires coming out of it, and then those 2 wires went to the next module, which had its own PCB inside of it, then, you know, if this plugged in somehow, right, like that, you know, this is not how you should treat products unless they're crappy, and this one is. So if those plugged in, you know, like that, this is again just a conceptual, right? You have a jumper, you could have a PCB, whatever. Then with that, you can now have an isolated serial bus that connects between each thing, and then that same 2-wire setup, you know, on the very end. So if this is the last module here, every module is connected there, could plug into a custom BSU, which my product is going to be called LI BSU. And now with those 2 wires, we can, with serial data, we know everything. We know the voltage, we know the current, we know the voltage of every single cell. So our global observer can see all of this data, and it can see temperature, and it can see, you know, the pack isolation to the chassis, and it can see the current, it can see all the things the BSU saw and a whole lot more. And the whole lot more is every single cell. That's the most important thing there. So that's kind of what I wanted to talk about. You really need a global observer here. And what does this global observer look like? None of these are a finished product. In fact, this is just a demo board that I bought years ago from Linear Tech, which is now part of Analog. But you can see if you squint a little, this is what you would put inside of your blade. Some version of this, and instead of using an RJ45, you just use a 2-pin connector, and all of your voltages would go there, and then you'd have the 2 wires. This would basically plug, you know, into their 2 wires, and then the next one would plug into the 2 wires of the next blade, etc. You'd have a huge daisy chain. And with that serial bus, each of your modules would have a circuit board. And to be honest, in the size of this circuit board here, you could probably fit all of this here, because a lot of this stuff is just test points because this is a demo board. But you could basically replace this circuit board, or, you know, design in the space of this circuit board something that went in there. And then inside of here, we have the connections here that go to each cell. And then the last one hooks up to my version of the BSU, LI BSU. This is, I've shown my product before, and I know no one cares about it, that's fine. This is the monolithic solution of that. So rather than having discrete boards inside of each thing and then, you know, an LI BSU product, this just does it all on one board. So this can measure 60 boards, 60 cells rather. And you can see that each little grouping here is one of these PCBs. There's another one, here's one, there's one as well. And then we have this logic board here, which would just become LIBSU. All of this stuff would go away. These are features that on this product for the Honda Insight won't exist in the Prius, because the Insight's more of an enthusiast car that likes things like current, you know, hacking and voltage spoofing and grid charging and all of those things that I don't think the Prius community cares that much about. My perception is that the Prius community basically wants to get in the car and they want to push the button and then they want to drive. I totally respect that. The Insight community is a little more adventurous. And so a lot of this stuff will go away on that product, on the LIBSU product. I have started working on the LIBSU product in earnest as of 2 days ago. So I know it's been a long time since I started it. I've been working on other stuff, mainly finishing this up here, which is getting very, very close, getting this product out of beta. The firmware is still not complete on it. This firmware will basically go over to the LIBSU product, which again, this is not, and this is the OEM product, some mashup of that or whatever, not even really, but my product is going to be mechanically identical footprint to the BSU. So my product will basically install in here, however that installs, and then it will have, instead of these 15 taps or whatever here, it'll just have 2 wires coming out, these 2 wires, and then these will plug into the first blade, and then the first blade will plug into the second blade, etc. I might have a round handler for error handling where there's actually 4 wires coming out of here, but this is conceptually, it's just an isolated serial bus. These are all low voltage, so all of these serial buses here are all low voltage. They're going to be internally isolated. In fact, there will be no high voltage inside of my LIBSU product. That will all be external to it. So all of the functionality that requires that, the OEM leakage, and then of course the battery voltages themselves will be contained within each module, however many modules there are. So we've talked about kind of what the game plan is there. Again, I've started working on that in earnest as of a couple of days ago. I basically started with the firmware where I picked up, I hadn't worked on it in a year, and I fully figured out the serial bus on the Gen 3 Prius, all of the weird ways that it sends data incorrectly that you just mirror because you're copying their product, or their serial protocol rather. But that is fully figured out at this point, and I hope to have that in a Gen 3 Prius on video soon. No promises there. I get very busy with things, and I am of course still working on this product as well. This is my higher priority because I have hundreds of customers that have this product. And yes, so the last thing I wanted to mention is I've talked about what is the minimum requirements to be safe, 1 wire, 2 wire, etc. I did want to point out that just because you have 1 or 2 wires connecting between modules, that doesn't mean it's actually safe. So this product here is Nextpower's V3. This is I guess a production unit. It has production cells. We've talked about it before, but it comes as 2 modules, so that meets my requirement, right? You have 2 or more modules, and it has this thing that has at least 2 wires. It has, I guess, 7 wires, and that plugs in, and then this plugs into the BSU, which I've lost. So this then plugs into your BSU, or it doesn't. I don't know, maybe it plugs in somewhere else. Whatever, right? Somehow this plugs in. I don't actually care how it is. This is not safe because if you look at this product, there is no logic, right? We are literally, it's this circuit all over again. I know I've talked about that before. All this is doing is hooking up the intermediate signals required for this. So this is not it. So it's just because you have 2 or more wires does not mean it's safe. This is definitely not a safe product, as I've droned on in multiple videos. So if you are curious to watch it, there's that. So yeah, that is kind of what the state of the lithium aftermarket and sodium aftermarket cells are for Toyota vehicles right now. As I said at the beginning, right now I am not aware of any safe aftermarket lithium or sodium product for any Toyota vehicle. If there is one and you're aware of it, I'd love to review it, so do let me know in the comments. I ultimately review all this stuff for public safety, public awareness. That is again why the company that I discussed here, I didn't mention their name, because they are making good faith efforts to fix these issues. We had a little back and forth initially about is it actually unsafe, and as soon as we were able to establish that yes it was, they went back and said we're going to go back to the drawing board, see what we can do. So yeah, that is that's this video. Thanks for watching.